Hello everyone, welcome to the lecture series on Foundations of Deep Learning Concepts and Applications. In the previous session we have started with autoencoder and variational autoencoders. This is the discussion for this particular week, and in the previous session we have seen the architecture of autoencoder, and then we have seen the reconstruction loss function, and here we have seen more in detail. We have seen mean square error, and we have just discussed about the binary cross entropy. In this particular session we will see the last two topics of autoencoder, which is types of autoencoders, and then we will see the key limitations of autoencoders. Now, when we are discussing the types, we will understand this through code level. We will also see, although we are not doing the hands on, since there are so many different types, but I will be teaching you how to write a code for each of these types. So, at a code level we will be discussing the various types. So, let us get started. So, the very first type of autoencoder is shallow autoencoder, and then what exactly what is the role of an autoencoder? We have already seen in the previous session that it has two objectives. The first objective is to get the latent space or latent representation, and the second objective is the reconstruction. So, when it comes to shallow autoencoder, the word shallow here is there is just only one hidden layer. So, which means you have an input, that input is passed to, let us assume we are dealing with an CSV file where we have an input of, we have features of totally 100, we have 100 features are there. Now, this 100 features are, let us assume this is 100 features. These 100 features are passed to the encoder, and what is the encoder here? Here we have only one hidden layer. Now, in that hidden layer, how many number of neurons? It is an hyperparameter. How many ever you decide, you will get so many number of output values. Suppose if we decide to have 25 neurons at an hidden layer, then what is happening? This 100 features are passed to an neuron which is having a 25, it is passed to an hidden layer having a 25 neurons. So, every of this 100 is passed to each of these neurons. Therefore, totally you will get 25 values as an output. Since there is only one hidden layer, the output of that is the latent space. So, this is a latent. This itself is the latent. Now, whatever is the output, this latent is now passed to an output layer. Now, how many number of neurons that you will place at an output? Since here it is 100, you are going to have 100 neurons at the output layer, so that you will get output 100 values. So, in short, what exactly is shallow autoencoders? In short, I will be calling it as AE henceforth. So, shallow AE here is the simplest form of autoencoder, characterized by there is only one hidden layer. Between the input and output, there is just only one hidden layer. And therefore, you see this entire part we call it as an encoder, and this part we call it as an decoder. So, architectural level, the input x is passed to hidden layer, and this is m is less than n. So, it is under complete architecture, and you are getting an output, and the dimension of the output and then the input should be the same. So, what you need to understand from shallow is there is only one hidden layer, and input is passed to hidden layer, and output of hidden layer is the latent representation that is passed as an input to the output layer. and you get the reconstructed one. So, let us understand this from a code level or from a practical perspective. Let us assume you have an input which is having 784, the dimension here is 784, and you are passing it to an encoder. Now, since there is only one hidden layer, that hidden layer we call it as an encoder. And how many neurons that you are placing here? 32 neurons. And dense. Why the word dense? Because it is fully connected, and because it is a hidden layer, the activation function used here is ReLU. So, how is that we will be writing the code? Can you see here? So, input the shape here is 784 one, that is passed to a variable inputs. So, that input is passed to a function called a simple underscore autoencoder. So, to this simple, where is the simple autoencoder? Can you see there is a function which is defined, and the name of that function is simple underscore autoencoder. So, for this what is being passed, this input is passed, which means 784 is passed here. So, this is now 784. Now, look at this, this is an encoder part, and how many neurons we have defined? 32. So, dense 32, activation is ReLU, and what is being passed? This inputs is passed. So, the output of this, how many you will get? 32 values we get, and that is a latent space. The 32 values what you are getting is the latent representation of this 784. Therefore, this entire is assigned to a variable called encoder underscore output. Why we are using encoder underscore output only? It is just a variable name. You can even write it as latent as well. Okay. Next, this latent is passed as an input to this layer. So, what is this layer? It is a layer where now you should get this 784 back, which means this is the hidden layer, this is the output layer which is having 784 neurons. So, you see this is a dense which is having 784 neurons, and for this what is the input, what input we are passing? This latent space which is having 32. So, that is assigned to encoder underscore output. So, the encoder underscore output is passed as an input to this layer, and what you are getting is a reconstructed output. So, decoder underscore output here is the reconstructed one. Okay. So, towards the end of this function, what we are returning? We are returning encoder underscore output and decoder underscore output. So, encoder underscore output is where you have an latent representation, and decoder underscore output is a reconstructed one. So, it is a reconstructed one. Now, I hope from the architecture perspective you have understood this. One important point that you need to understand here is why they have used sigmoid. Now, you can ask the question from ANN or from our traditional deep neural networks, what we have seen, if you are solving a classification problem, and more specifically if you are solving a binary class, you will use a sigmoid as an activation output activation function. If you are going for a multi-class classification, at an output layer you will be using softmax. Then if you are predicting a number, if you are solving a regression kind of a problem, then the output activation function will be linear. But autoencoders are something which is an unsupervised, which means these are the architectures which are built not for any classification or regression. If that is the case, then why is that we are still using a sigmoid? So, most important concept, please focus here. So, at an output layer, we are using a sigmoid. Why is that we have to use a sigmoid, and is it that sigmoid is the only thing that we have to use? Look into it more important. Now, at the end of this, what is our aim? Our aim is to reconstruct the input back. That's the ultimate aim. Now, during a pre-processing stage, if at all if you have changed the input to some other representation, what is the meaning of it? What if the values are scaled between 0 and 1? If you are using min-max scalar, the value will be between 0 to 1 only. All the values will range between 0 to 1, so that you can avoid bias. Now, what if you use standardization? What if you are not using any pre-processing? So, this sigmoid actually depends on during a pre-processing what measure that you have taken. Say for example, you have an input data and in that there are some values and because the minute you say you are using a dense, it means all are converted into, you are building a fully connected neural network. So, here the values can be anything. In order to avoid unintentional bias, so what we are doing, we are applying min-max scalar. Now, when you are applying min-max scalar, is it not all the values are now between 0 to 1 only? What is min-max scalar? X minus go back, it is x min, then x max minus x min. So, this is what is the formula for min-max scalar. Now, when you have this kind, you have already changed your data and you brought your entire data back to 0 to 1. So, you have changed the value back to 0 to 1. If that is the case, is it not when you are reconstructing the value, when you are reconstructing the output, is it not that the value should be again 0 and 1 only? Whatever the value that you are going to get, is it not that value should match to an input? Then only you will say that your input is matching to an output. So, which means your output values what you are getting also should be in a range between 0 to 1. So, how is that it is possible? It is possible only with the sigmoid activation function. Therefore, we are using activation equal to sigmoid. I hope this is clear to you. This sigmoid is nothing to do with the classification, binary classification, nothing to do with that. It is only to match with the range of input values. Suppose if the input value used, you have used min-max scalar and changed the values between 0 and 1, then whatever the reconstructed values that you have got also should be in that range only. Therefore, we have used sigmoid. Now, you can ask the question, ma'am, what if we are not using any normalization technique, standardization technique, we have not used any of those pre-processing, as it is the raw values we are using, then this activation will be linear. So, make a note of it, activation will be linear, or the activation or not necessarily this. What if you have a value between -1 to 1? Suppose if you have used an standardization technique, then also you will be using a linear activation function. So, sigmoid you will use because you have changed the value between 0 to 1 at an input. Therefore, at a reconstruction also you should get these values only. Therefore, activation equal to sigmoid, but nothing to do with classification problem here. I hope this is clear to you. That is what has been written here. At a decoder output, the reconstructed value must match the range of the input data. Therefore, in a pre-processing, if the features are scaled to 0 to 1, then we typically use a sigmoid activation. Then because we have used a sigmoid activation, later we have to go for model.compile. There you will be using a binary cross entropy loss. If the input features are unscaled or standardization, then a linear activation function is used and the MSE loss will be used, mean square linear activation and mean square error. loss function. Okay. Now, next important point that you need to understand here is what will happen. Why is that? So far we have written a code as model equal to sequential, and inside that we had written dense layers. Why is that here we have not written it as model equal to sequential? The only reason here is ultimately what is that you want to visualize? You want to visualize the latent space. This we want to see, and also we want to see the output. This is all is our requirement, right? We want to see the latent space and latent representation and then reconstructed one. So, where do we get this latent? For this shallow encoder, latent representation is this, reconstructed output is this. In order to visualize, in order to get these values, we are writing a code in the form of a function. That is all. Not that you should not write model equal to sequential, but here we want these two values explicitly, right? Yeah. So, let us proceed with the next type of autoencoder, which is an deep AE. Now, it is there in the name itself, deep autoencoder. What is a deep autoencoder? It is an extension of shallow encoder, where you just do not have one hidden layer, you will now have multiple hidden layers. Yeah, you can have any number of hidden layers, but the last hidden layer output will be the latent representation. So, here if you take, there are two hidden layers. So, the output of this hidden layer will be the latent representation. So, so there will be an since there are three, there will be three latent representations here, and from here you will be passing it to hidden layers of decoder. So, here you see there are more than one hidden layer. When you have multiple hidden layers, we call it as an deep autoencoders. So, let us see this. You see the example, we are extending the same example of shallow. In the shallow we had taken 784 and there was just only one hidden layer, but here since the word it is deep, you will have multiple hidden layers. So, how many such hidden layers are there? There are three such hidden layers, hidden layer 1, hidden layer 2, hidden layer 3. Whatever is the output, this is the last hidden layer, right? So, the output of last hidden layer is the latent representation. Since there are 32 neurons, the latent representation also will have 32. Then this 32 is passed to decoder, which is having again at a decoder side, this is the first hidden layer, second hidden layer, third hidden layer, and you see input is 784 and the output of last hidden layer also should give us 784, which means this hidden layer should have 784 number of neurons. So, what is the aim of an autoencoder, and more specifically the encoder part? It should have decreasing number of units in the hidden layer. So, therefore, you have 128, then 64, then 32. Is it that always it is fixed? The answer is no. You can this is an hyperparameter, you can have any value, but ensure have it in the decreasing order. At a decoder part, you have to go in the increasing order because aim is to reconstruct back. So, from 32 you are going it to 64, from 64 to 128, 128 to 784. I hope the architecture is clear to you. So, now let us see the code how we are writing. So, we have 784 input. This input is assigned to this variable and you are calling a deep autoencoder function. So, the control is going to this particular function. Here this is the first hidden layer. Let me clear everything. Okay, we are passing it to first hidden layer. So, how many units are there? Neurons are there, 128. Activation function is ReLU and the input is being passed and it is assigned to variable x. For the next hidden layer, x is passed as an input. This x is passed as an input. Can you see here? And how many, this is second hidden layer which has 64 neurons. So, second hidden layer ReLU, because of dense it is fully connected one, and you are going to get one output. That output here is assigned to X. So, which means X is passed to the third hidden layer which is having 32 neurons. Third hidden layer 32 neurons, activation is ReLU, and this X is passed here. Now, whatever we have obtained, that the output of that is the latent space. So, the output here is latent. Now, this latent is passed as an input to a decoder. Okay, latent is passed as an input to a decoder. Can you see latent? How many neurons are there? 64. 64, activation is ReLU, and that is assigned to variable X. So, something we get output 64 which is X, that X is assigned here, and then you are passing it to 128, and the output is X. So, which means 128 which is X. So, that is assigned to that is passed here. This 128 neurons is now passed to 784. So, 128 784. So, you finally get 784 values as an output, that is reconstruction. So, this is how you will code the deep autoencoder, and the concept here is you will have multiple hidden layers. The difference between shallow and deep, in shallow you have just one hidden layer, and in deep you have multiple hidden layers. Third variant, which is called conventional autoencoder, which is very important. Please focus here. So far what we have seen is a linear autoencoder, which means you are working on a CSV file. Suppose you have a data which is in the form of a CSV file. Now, what if your data is an image? What if you want to reconstruct an image? Then you have to go for a conventional autoencoder. So, the minute you say conventional autoencoder, it is exactly same. What came to your mind is CNN, right? So, most of the concepts is exactly same as the CNN only. So, let us see what exactly is a conventional autoencoder. First point, the input is an image. So, here whenever your input data is an image, then and your aim is to reconstruct, then you will go for a conventional autoencoder. Now, so here also you have an input, this is input, then this entire part is an encoder. So, up to the output of encoder will be the latent space. The latent space is passed to decoder, and then you are going to get a reconstructed image. So, here also you have an encoder, latent representation, and a decoder. So, what is the encoder here? Encoder is exactly same as our CNN, where you will have a convolutional layer and you will have a pooling layer. Here more specifically we will go for max pooling. So, at the encoder part it is convolutional layer and max pooling is what we are going to have as an encoder. Now, whatever you have written at the end, the last layer, it can be an convolutional layer or it can be an max pooling. Whatever is the last layer that you have defined, the output of that will be your latent space. In our CNN, what we were doing, the output of last layer, which can be either convolutional layer or it can be pooling, we were converting that into flatten. So, here we are nowhere using any flatten layer. The output of the last convolutional, which will be in the form of a feature maps only, we will still have in the form of a feature maps. That is the latent space representation. So, the output of a final convolutional layer in the encoder serves as a compressed representation, which is a latent space. That is passed to a decoder, and at a decoder two things are possible. Either use transpose convolutional or conv transpose, or it is upsampling plus convolution. So, whenever you see at a decoder, you will either perform this operation or you will perform this operation. Let us see later in this slide which one we are using, but what you have to understand from this particular slide is, whenever we are dealing with an image, then we have to go for an convolutional autoencoder. Whenever you say autoencoder, you have an encoder, latent space, and then we have decoder. Now, what is encoder? Encoder is a convolution operation and max pooling. Whatever is the last layer that we have defined, that last layer output will be the latent space. If the last layer in the encoder is convolution, then the feature maps of that last layer will be the latent space. If the last layer is a max pooling, then the feature maps of max pooling will be the latent space. Here we are not using a flatten. Please note, we are not using a flatten. So, we are working with the feature maps only, and the decoder is either it is a transposed convolution or it is upsampling plus a convolution. We will see any one of this we will be using, but which is more specifically we will be using, we will understand in coming slides. So, look at this, this entire part is DNN here is a deep neural network autoencoder, and the second part what we are seeing is a convolutional autoencoder. Now, you can ask the question, ma'am, why is that we have to go for a convolutional autoencoder? Why can't we deal with deep neural network only? Why deep autoencoders will not work? The answer is, in deep, you are flattening the image. 28 cross 28 will be flattened into 784. So, the minute you flatten, the spatial information is lost. When the spatial information is lost, then you, whatever the reconstructed image that you are going to get will not be of high quality one, will not be of good quality images. So, when you look into, so that is the drawback here in deep, because you are passing all the information to an fully connected neural network. So, you cannot pass as an image, it has to be into a single vector. So, if you are passing it as a single vector, then the matrix which is 28 cross 28, which is in the form of rows and columns, is being lost, which means the spatial relationship, the edges, the contours, the shapes are being lost here. That is the reason you see this is the input, this is the latent representation, and this is the output. Can you see the clarity? Can you look into this? This is the input and this is the output. Look at this, there is something inside this, but the model has not been able to capture. So, look into each of this, look into the one which is highlighted in red, there is a lot of blurriness. We are not able to visualize, the reconstructed image is not matching with the original one. That is the reason we are going with CNN based autoencoder. Why CNN based? Are we using anywhere flatten layer there? So, if you go back, have you used anywhere flatten here? No, we are dealing with the feature maps only. This latent space will have the feature maps of the last layer in encoder. So, because we are using convolution, therefore, we are preserving all the local spatial structures, which means it is able to learn the edges, textures, shapes, and the decoder is going to learn from these feature maps. Therefore, you look into the highlighted in red, look into this part and look into this. So, can you see here the clarity is more, the clarity is high comparing to this one. And look at this here, this output and this output you look into. So, here you can able to see a better feature extraction. That is the reason do not go with the deep autoencoders when you are dealing with an images. It has to be an convolutional based autoencoder. If that is the case, how is that we will be writing the code? Look at the way that we are writing the code here. The input is 28 cross 28 into 1. Okay. So, here the input is 28, 28 to 1, that input is been passed to the first convolution layer, and in the first convolution layer there are 64 filters. There are 64 filters or kernels, each of size 3 cross 3, and the activation is a ReLU, and padding equal to same. When you write padding equal to same, whatever the input size, it is the same input is retained. Input is 28 to 28, therefore 28, 28 is retained. That is assigned to one variable. That variable is passed to an pooling layer. So, pooling layer you are writing 2 cross 2. So, which means you are downsampling it, you are reducing the size, therefore, and exactly by half, 28, 28 is now reduced to 14, 14, and because you have it is assigned to this particular variable, and this value is assigned to the next convolution. And in the next convolution you see the padding equal to same. Therefore, here you have changed to 28, 28 has now reduced to 14, 14, because the padding equal to same, you still have 14 cross 14. And then how many kernels you have used? 128 kernels, you got 128 here. Right. Then you have assigned it to one variable, that is passed to the pooling layer, and in pooling you have used 2 cross 2. So, exactly it will be reduced by half, which is 7 cross 7. So, you have 7 cross 7. This is last pooled output. So, that is assigned here, and then what you are doing? You are defining one more convolution operation. So, what is that one more convolution layer? So, after pooling we are defining one more convolution, which is having 256. So, whatever, and to this what input you are passing, the last pooling is passed as an input to this convolution, and this operation output what you are getting is the latent. So, which means the latent here is 7 cross 7 cross 256. I hope this is clear to you. Now, this is all with respect to encoder. Now, let us understand what will happen at the decoder. So, at a decoder, it is upsampling. So, what is upsampling? Your ultimate aim is, here you have reduced to 7 cross 7. From 28 cross 28, we have reduced to 14 cross 14. From 14 cross 14, we have further reduced to 7 cross 7. Now, from here, from 7 cross 7, your ultimate aim is to go back to 28 cross 28, which means you have to now do upsampling. How is that you do upsampling? Whatever is the output of the last layer, it can be a convolution layer or it can be an pooling layer, but here in our example, the last layer here is a convolution. So, definitely the size is smaller. Why the size is smaller? Because over a period of time when you have gone through series of layers, the size has reduced. Now, from this you should ultimately go back. So, which means you have to now perform upsampling. So, what is upsampling? It increases the spatial resolution. What all different ways you can do upsampling? So, the first method what we have here is, let us assume this is x, which is 1, 2, 3, 4, which is just an let us assume this is the x. Just for understanding the upsampling technique, we have taken a smaller dimensional input, and s is sampling factor. Here sampling factor s is equal to 2. What is the meaning of this? Each of the element in x should be expanded by 2. What does it mean? Now, each element, I have the first element is 1, should be expanded 2. So, because sampling size is 2, so each element is copied into 2 cross 2 blocks, which means I can now write 1 1 1 1. Is it now not 2 cross 2? Now, the second element is 2, again 2, because S is 2, each element is copied into 2 cross 2. So, it is 2 2 2 2, which is 2 cross 2. Then the third element is 3. The third element, because S is equal to 2, it is expanded 2 cross 2. Then fourth element, it is 4 4 4 4. So, is it not 2 cross 2 now has increased to 4 cross 4, right? This is called upsampling, where in upsampling, when you expand, if you put each element as 1, here each element as 2, element as 3, element as 4, then we call it as nearest neighbor upsampling. Okay. Then instead of y1, what if you fill all zeros, which means you have 1, all values will be 0. Then you have 2, all values are 0. We have 3, all values are 0. We have 4, all values are 0. Then we call it as bed of nails upsampling, which is called zero insertion. So, this is an upsampling technique. One is nearest neighbor upsampling, second is bed of nails upsampling. What is the main drawback of this? If you look into the main is there anything to learn here? It is just take the values and increase the value, increase. You know, there is no learning at all here. So, because of this, you know, no learnable parameters are involved here. Yeah, it is just taking 1 and then inserting. It is taking 1, inserting all zeros. So, there is no learnable parameters here. So, this is what is upsampling. So, let us now see what is transposed convolution operation. Because at a decoder, ultimate aim is to reconstruct back, which means you have to increase the size. Now, we have seen if you use upsampling, there is no learnable parameters here. Now, let us see how it is happening in transposed convolution operation. In transposed convolution operation, let us assume we are taking one input, let that input be 1 2 0 1 just for understanding, and then we are going for an kernel. Now, what kernel we are using? We have to use an flipped kernel here. What is a flipped kernel? Whatever is the kernel values that we have, you know, change those values, rotate those values by 180 degrees. This is the kernel values that we have. Even if you do not go with this, so just understand there is a kernel that is given, and in that kernel there are some values. If the size of the kernel is 2 cross 2, we have 2 cross 2 values. What is a transposed convolution? Input is multiplied with the kernel. If this word is confusing you, just remember it as there is a kernel given and then input is getting multiplied with the kernel. So, how is that input gets multiplied? What is the size here? What will be the output size? You see input is 2 cross 2 and the kernel is 2 cross 2, and what will be the output size? It is input plus kernel minus 1. Input value is 2, kernel value is 2 minus 1. So, 2 plus 2 is 4, minus 1 is 3. So, 2 cross 2 input is now upsampling is increasing the size. We have increased to 3 cross 3. How is that you are increasing to 3 cross 3? Initially all the values will be 0. Okay. Now, you will take the input, first input, 1 gets multiplied with all of this, 1 gets multiplied, so this becomes 4, 1 gets multiplied, this becomes 3, 0 and 1 is 1. So, this is the value that you get when you multiply 1 with the kernel. So, I hope this part is clear to you how we have done it. Then next is you will take the next input. What is the next input? It is 2. 2 gets multiplied with each of these elements. So, when 2 gets multiplied, it is 4 2s are 8. So, here it will be already you have 4, 3, 0, 0, 1, 0, 0, 0, 0. Now 2 gets multiplied with each of these elements. So 4 2s are 8. This value will be 8, and already you have 3. So it is 8 plus 3. Then 2 gets 3 2s are 6. Then this value will be 0, and 0 gets multiplied with 2 is 0. 0 plus 1 is 1, and 1, and for this it is 1. So you see, the next value when you multiply, 2 is multiplied with each of these elements. I am sorry, let us go back. 1 gets multiplied with each of these elements, you get this. 2 is multiplied with each of these elements, not respective. So 2 gets multiplied with each of these elements. So 4 2s are 8, 3 2s are 6, 2 2s are 4, and 2 1s are 2. Similar way, you take 0 gets multiplied with each of the element, 1 gets multiplied with each of these elements. Then what you are going to do, you are going to add all of these values. So what is G1? G1 is this, G2, G3 and G4. You will take each of these values and then you will add. So is it not, earlier input is 2 cross 2, now the 2 cross 2 is now converted to change it to 3 cross 3. This is upsampling. I mean, this is definitely you have increased the size. And what is this operation? It is a transposed convolution operation. There is one drawback of this. What is the drawback? When I was calculating, have you observed, for the first time it was 4 3 0 2 1 0 0 0 0. Second 4 2s are 8. This 8 is here. 8 is here. So 8 is getting added with the 3. This 8 gets added with this 3, and you got this value. So middle values are getting more visibility again and again. So transposed convolution operation leads to a problem called as an checkerboard problem. What is a checkerboard problem? Can you look into this? Can you see there is a grid like pattern here, which has an alternative bright and dark. There is a square kind of a patterns that we are getting. There is an uneven texture, and so there is a kind of a box squares which you can able to see it. So why this is happening? Because when you are performing, the middle elements is automatically getting added again and again. So middle regions are getting more visibility. So because of this, it is not a noise or it is not an error. The operation itself will add some sort of an bias here. This is not a noise. It is an systematic artifacts which are caused by the operation itself, and this kind of a problem we call it as a checkerboard problem. So upsampling does not have anything to learn, and transposed convolution has this checkerboard problem. Therefore what operation we have to do at a decoder side is upsampling and convolution. So what is upsampling here? So first step, you have input 1 2 0 1, do the upsampling. So how is that you do upsampling? It is nearest neighbor 1. And whatever is the matrix that we have obtained, on this you apply convolution. What is a convolution? Since it is 2 cross 2, first you do multiplication with this and this, you will do a point wise element wise multiplication and addition, convolution operation. You see, you are doing element wise multiplication and addition. Then you will do a stride, then you will take these values, you will multiply it with the kernel, then so that value is this. Again you will do a stride, you will take this, multiply with this, it is this value. Then you will come down, you will take this value, multiply it with the kernel, stride, so on so forth. So here by going for upsampling and convolution, you are first upsampling first spreads values uniformly, and then subsequent convolution applies the kernel evenly. So, this avoids that checkerboard artifacts. Therefore, in convolutional autoencoders, it is not transposed convolution that we apply upsampling and convolution we apply. So, look at this. So, at a decoder side, how do we write a code? We first use upsampling and then we use convolution. So, we again do upsampling, then a convolution, upsampling, convolution, upsampling, convolution. So, what upsampling will do? It is going to increase the size. Can you see? 7 cross 7 has now increased to 14 cross 14. Then here upsampling 14 cross 14 has increased to 28 cross 28. But the last convolution still has number of kernels. So, therefore, now ultimately we want back to one channel. This is 64, 21, 28, 28, 64. Now, you want to change it to 1. Therefore, you have passed it to one more convolution operation where the number of kernel here is 1. Therefore, you get 28, 28, 1. So, this is a reconstructed one, and output is bottleneck, or it can be an latent and reconstruction. So, this is how you will code for convolution autoencoder. However, we will be seeing all this in the hands-on, but this is how the convolution. Once again, we are using a sigmoid here. Why sigmoid? Because maybe in the input we have here we have resized or rescaled values. You would have divided each of these pixel values by 1. All the values will be between 0 and 1. So, when you have reconstructed, the value range should match. Therefore, we have used sigmoid. Now, the most important here is latent space dimensionality. Now, whenever we are defining the latent space, this latent space, although it is an hyperparameter, we should ensure that we have to control this, we have to fine tune this properly, because if the latent space size is too low or it is very small, then reconstructed value or reconstructed output quality will be very, very poor. It leads to a poor reconstruction values. But at the same time, if you keep this and higher value gives a good latent space, and good latent space gives us a good reconstructed value. But just because it is giving a good, if you keep a larger value, then also it gives us the diminishing returns or the result. Therefore, this latent space is the most crucial part in the autoencoder. Too small, too large value is a problem. Therefore, you have to control this, because the latent space dimensionality controls the reconstruction quality. And the last type here is denoising autoencoder. And denoising autoencoder, it is mainly the input what is given to it is an noisy input. You see here the input, there is lot of noise which is present, and the main aim of denoising autoencoder is to remove the noise from its input. Whatever is the noise that is being added, it is just focuses on removing the noise. So, instead of learning to reconstruct the input, it only learns to reconstruct the original input from the corrupted version here. So, this is what is the denoising, and these are the various outputs. We will be seeing this in our hands-on also. We will see that this is a noisy one, and this is the denoisy image. So, if you have this kind of an application, then we will be going for denoising autoencoders. So, with this we have come to an end of this particular session, where we have seen autoencoders, and in the next session we will see variational autoencoders, and then we will see its architecture and then the loss function. Thank you.